In these Chapter 11 and 12 review problems, we're asked to demonstrate our knowledge of alcohol physical properties, structure, nomenclature, and some mechanisms. The first question is asking us about alcohol nomenclature. So we're given the name 4-methyl-1-cyclohexanol. So we're asked to draw that structure. Anytime you're given a name and asked to provide the structure, you want to find out what the base carbon chain is. So in this case, it's going to be a cyclohexane. We're going to go ahead and draw that. That's the 6-membered carbon chain. The major functional group is given by this suffix OL, which is an alcohol. This number is a locant, which will tell us where that functional group is. I've arbitrarily put it on this carbon, so that's going to be our 1 carbon. So we've effectively answered this part of the question. Now we're moving to the left to the next substituent, which is 4-methyl. So we're going to start from our C1, C2, C3, and C4. Here we're going to draw our methyl group. So there's our 4-methyl-1-cyclohexanol. The next question gets a little more involved in that we're asked to include stereochemistry in our answer. Again, we're asked to draw a molecule, but this time it has a descriptor which is S. The parent chain is butane, so that's the C4 carbon chain. The suffix is OL. That's the alcohol at position 2. And now it's asking us to show the S stereochemistry. We assign R and S based on priority of the groups. So for R stereochemistry, when the lowest priority group is projected behind us, the priority moves in a clockwise fashion. For S, it moves in a counterclockwise fashion. So I've drawn in what R and what S need to be. So to show that in this molecule, we have to use either the wedge or the dash to figure out what's going on. So R and S is assigned on priority, which is based on the atomic number from the periodic table. So here's our stereogenic center at this carbon. We need to basically give each of the substituents a number. So we have oxygen, hydrogen, carbon, and carbon. Oxygen is going to have the greatest priority. And then we can go ahead and assign the lowest priority to hydrogen. So now we're given a choice in that we have 2 carbons. We have a methyl group and an ethyl group. The ethyl group is going to get priority 2 because when we go out, the 2 carbons are equivalent. This carbon only has hydrogen. This carbon has another carbon. So here's our rotation. Now if we put 4 projected behind the plane, that's going to give us an R designation. 1, 2, 3. So we're going that way if 4 is behind us. If 4 is projected out towards us, we have to reverse that designation and we'll end up with the proper answer. 1, 2, 3, and then 4 is towards us, so we reverse it to get S. To redraw that in a more clear way, we can actually put the OH behind the plane of the board. There's our hydrogen. Now we have 1, 2, 3, initially giving us R, but because the lowest priority group is projected towards us, we reverse to get S at C2. The third question is predict the product. We're taking a tertiary alcohol treating that with strong acid, sulfuric acid, in the presence of heat. So we should recognize that an alcohol with acid and heat is going to do a dehydration. So this is going to proceed via protonation of the hydroxyl group. Water then leaves to form a carbocation. And now for the elimination. We want to do an elimination so that we form the most stable alkene. And we're going to do that from a carbon bearing the least amount of hydrogens. So that's going to be this carbon here next to the carbocation. So when we do that, we'll end up with the following alkene. There's our double bond. You can see this is a tri-substituted alkene. If we eliminate a hydrogen from this methyl group or that methyl group, we end up with a di-substituted alkene. So in alkene stability, the more carbons you have on the CC double bond, the more stable it is. Our next question is an acid-base question. We are given ethanol in the presence of sodium hydride. So this we should recognize as a base. We have ethanol with an acidic proton in the presence of a base. So we're going to abstract that proton. Sodium is our counterion, and our byproduct is hydrogen gas, which is evolved from the reaction. Finally, our fifth question is asking us about hydrogen bonding. So if you were given these four compounds and ask which one can both accept and donate a hydrogen bond, you need to recall that the only situations where that's possible are when the molecule has an OH, an NH, or HF, which is its own unique compound. So this is its own compound. These can be substructures in molecules that we know. So if we examine these structures, we have an alcohol, an ether, and an alkane. So only this alcohol can both donate and accept hydrogen bonding. So what implications does that have? If you were asked to determine which of these is going to have the highest boiling point, it is going to be the one that can hydrogen bond. And remember that hydrogen bonding is an intermolecular force. So that's going to increase the boiling point of ethanol relative to the other compounds. So that's a review of some concepts from chapters 11 and 12. And in the next video, we'll talk about some more complicated topics.